Hi, my name is Audrey Olenski, and this is my presentation of Lab 4, Studying Circuits and Capacitors. I will begin with an introduction to the lab. In studying circuits in this lab, we rely on multiple key physics concepts to make sense of our data and observations. The first is conservation of energy, which states that no energy can be created or destroyed within a system. The second is similar to the first, which is current conservation. This experiment also depends on the loop rule, which states that the potential difference around a loop is zero. Lastly, we'll use the equation seen on the right that states that current is equal to the change in electric potential divided by the resistance. Our purpose in doing this lab is multifaceted. First, we will use it to predict the behavior of circuits that have resistors in series and in parallel. Additionally, we will use multimeters to measure current and potential difference around the circuit. Lastly, our purpose is to observe how different circuit elements, such as ohmic resistors and capacitors, affect the circuit's readings. For this lab, we used the PHYS Circuit Construction Kit Virtual Lab Simulator to build and test our circuits. For the first experiment, I created a simple circuit in series with two 1.5 volt batteries, 2 ammeters, and 2 ohmic resistors of 47 and 100 ohms. Using the current equation from above, I was able to predict that current 1 and current 2 were 0.02 amps. This matched the reading in the simulator as seen in the top picture. When the ammeter was flipped backwards, the reading was still 0.02 amps. When I replaced one of the ammeters with a voltmeter, the reading on the voltmeter was 3.0 volts and the ammeter reading was 0. This is because the voltmeter has a very high internal resistance, so no current can pass through it. Next, I removed the top ammeter and closed the circuit. I then measured the potential difference across each element of the circuit as seen in the picture on the right-hand side. When these individual potential differences were summed, they came to 0. This is what we would predict, as we know that the round-trip potential difference, no matter the path, will always be 0. Here you can see a visual representation of how the voltage starts and ends at 0 across the circuit. As predicted, the voltage drops from C to D and E to F, where the resistors are placed. Finally, we can calculate the resistance of each of the circuit elements shown using the potential difference in current values. By rearranging our current equation, we can calculate resistance by dividing potential difference by current. Part 2 of this experiment looks at RC circuits. Here I built two circuits with a 200 millifarad capacitor, a 9 volt battery, and a 10 or 20 ohm light bulb. I noticed that when connected, the light starts bright and then dims as the capacitor charges. The opposite happens when the battery is removed and the circuit is closed with a wire, as the capacitor discharges. From the charging and discharging times on the right, we conclude that capacitors take longer to charge and discharge when the circuit's resistance is greater, because here the 20 ohm times are greater than that of the 10 ohm resistance bulb. In part 3 of this lab, I increased the resistance of the bulb to 30 ohms. For this circuit, we know that the potential difference of the capacitor and the resistor sums to 0. Using what we know about current and energy, we can rewrite the energy conservation equation to be Q over RC plus dQ over dt equals 0. Through solving the differential equation, we can get the final equation, which states that the natural log of the potential difference over the initial potential difference equals negative T over RC. RC is the time constant of the circuit, a measure of the time it takes for the voltage difference to drop 1 over E of its original value. When we plot both sides of the equation against each other, the slope of the line is negative 1 over RC. Here you can see these two plotted against each other on the right. To produce this graph, I measured the voltage of the circuit for 20 seconds while it was discharging, collecting data in 1-second intervals. I then took the natural log of this voltage divided by 9, the initial voltage, to produce the data. Here the RC time constant is 6 seconds. To conclude this discussion, I am going to discuss a few questions regarding how this lab applies to real-life circuits. The first is how the circuit would be affected by a real-life ammeter. This simulation assumes that the resistance in the ammeter is 0. However, real ammeters have some resistance greater than 0. Because of this, the current would be a bit lower than what we observe. Additionally, if we used a real battery, charging and discharging times would increase compared to those in the simulation because real-life batteries also have a non-zero resistance. This concludes my discussion of Lab 4. Thanks for listening.